Welcome back. So we have discussed finite field, and about quadratic we have stated and proved Gauss's law of quadratic reciprocity. And so today we discuss a slightly different topic, which will be useful to us later as the course goes on. So let F be a field. Let F be a field, and I is a subset of fx, the polynomial ring in one variable over the field x. So this is a subset of fx. Then the zero set of I, vi, is a subset of f and is defined as vi to be the set of elements in the field f, such that also called variety of I is the set of elements in f such that f is a root of f for all f belonging to I. Okay, for all polynomial fx which belongs to I. Okay, so I'll repeat. V of I is a collection of elements in f, those elements in f, such that it is a common root of all the polynomials f in I. Okay, where I could be any subset of fx. So let us right away to understand the definition better. So the key point in some sense here is for all f. Okay, so it is in some sense the intersection of the zeros of all the polynomials. So let us assume that uh, so let us take a special case that I is an ideal in fx. So I took any subset here. Now you take I to be an ideal in the polynomial ring fx. Okay, so assume I is an ideal. Then there is a monic polynomial hx, so fx is a principal ideal domain. F is a field, any field, and fx is the principal ideal. Fx is a polynomial ring in one variable over x. Then we know that fx is a principal ideal domain. So every ideal is singly generated. So if I is the subset is an ideal, then it is generated by some hx, and without loss of generality, we can assume hx to be monic. So suppose the leading coefficient is a. So suppose hx equal to a0 x to the power n plus a1 x to the power n minus 1 plus something lower degree polynomial where ai belongs to f and a0 is not equal to 0. Then you multiply by a0 inverse hx. A0 is a unit in the field, right? So this ideal is the same as the ideal generated by hx. So that is why, without any loss of generality, we may assume that it is generated by a monic polynomial. So if the highest degree coefficient is there, it is an element of the field and it's non-zero. So it has an inverse. Multiply it by the inverse. The ideal doesn't change because if you multiply by unit, the ideal remains the same. So we can assume it is generated by a monic polynomial. And in fact, we are not using even monic here. In fact, so the variety, so so the variety of I is the set of zeros of the polynomial, set of a in f such that f of a equal to 0. So think about it, because every element here in this ideal, every element looks like, so if g belongs to gx belongs to ideal gen by hx, then gx equal to looks like some fx times uh, some tx, right? So every ideal is a multiple of fx. So if it is true for all, gx. So f of a. So if you look at this elements a in f, so they vanish at all g, which are multiply, which are all gx, which are multiple of fx. They vanish at this point. So this is clearly this contains this, right? Those roots of f, those elements where a vanishes, uh, every element of I will vanish. So this contains this one. On the other hand, it is easy to see if something is in Vi, then every polynomial should vanish here. In particular, F should vanish here at all. So if there is a point which is not a root of A, okay, so if there exists B in F such that F of B is not equal to 0, then obviously you look at the element F itself in the ideal I, right? Then B is not there. So this is contained inside this, and if an element is not there, it is not in the ideal. So that means ideal is also contained inside this, right? Okay. So the ideal V of I is equal to this. So here, let's take for simplicity, I should also add a condition that I, so let's just say 0 strictly contained in I. Okay, so here maybe I should put a condition that that assumes that I is an ideal in Fx. So okay, so maybe I should change it a little bit. Need some additional. I'm going to discuss it what I'm in a moment. So let me just make some changes. Assume that assume that that 0 strictly contained in R, strictly contained in Fx. Okay, so I is not equal to 0, not equal to whole ideal. Then what I said is true, and more generally V of 1. So next, what happens in the case? So this is a special case of an ideal, which is so basically we are talking about what is V of I. Is essentially we are talking about zero set of some polynomials. Okay, so the set of elements where this vanishes, we are talking about that basically. And so, for example, what is V of Fx? Whole ring. Okay, and I'm claiming this is the empty set. Okay, so why? Because this contains one, and if it contains one, then it is those elements where one vanishes. But so any non-constant polynomial doesn't vanish at any point, so this has to be equal to that. What is on the other end? What is V of 0? The identically 0 polynomial. That is equal to, so this will be true for any unit, right? So ideal general by any unit, or if I take this just the subset 1, then V of, we see that V of 1 is V of Fx is the empty set. V of 0 is in the entire field F, because it's identically 0. We are talking about those points where the identically 0 function vanishes, and that's at any point. So these two are trivially true. And in fact, V of n subset I is the, uh, so more generally, what I want to say more generally, for a subset I of I of I of Fx, we have that V of I is actually V of uh, this ideal generated by I, where this denotes the ideal generated by the subset I. So given any subset, we can consider the ideal generated by it. So it is the ideal generated by. So of subset is same as the ideal generated by that. So let's see some more concrete examples. So for our better understanding, so let's say the field we are talking about, field is R, and you have the polynomial x squared plus 1, the subset to be the singleton element, x squared plus 1, or equivalently, you can talk about the ideal generated by x squared plus 1, we just saw. And that's so this is exercise, it's not difficult to prove that by definition of ideal generator, so every element will be a combination by R multiple of elements of the cell set I. So if something vanishes on I, then you can see these two sets are equal. So for example, f equal to R, you take the polynomial x square plus 1, this is a reducible polynomial over Rx. Then R and so then v of this is empty. For example, x to the power 4 plus 1 also it will be empty, and so on. Okay. So so this will be empty, and uh, so and on the other hand, if you take x square minus 1, then the zero set of x square minus 1 will be 1 and minus 1, right? If you take x square minus 2, it will be root 2 and minus root 2. So the what field we are talking about is really important here. So you have to specify the field. For example, if you take f equal to c instead of r, and you ask about the same polynomial, x square plus 1, then the zero set is iota and minus iota, right? Where iota square equal to minus 1. So since this is the irreducible polynomial, it has no root. So this zero set of it, this is empty. Similarly, like you take x square plus 1 over c, but then the answer changes. It has root iota and minus iota. And similarly here, x square minus 2, you saw it has root. So the zero set is root 2 and minus root 2, but over q, the zero set is empty. So when you are talking about zero set, which field you are talking about is important. Okay. So these are some of the properties. So we have seen the V of the entire ring is the empty set. Polynomial ring in one variable is the empty set. V of zero ideal or the zero element is the whole all of F, and V of ideal of subset is same as the V of the ideal in that subset. And if if I is a subset of J, then you can see this is reverse inclusion. So V of J will be subset of V of I. So bigger the ideal, the subset will be smaller. So indeed, when you had zero ideal, the smallest ideal, the zero set was entire F. And when you took the biggest ideal, namely all of the ring, then the zero set was the empty set. And you take if I is a subset of J, then you can see you can prove Vj is a subset of V of I, and Vi intersection Vj. If you take zero set of two subset I and J, that is nothing but. So again, so by this property, we can assume them to be actually ideal. So if you take V of two ideals I and J, then V of I intersection V of J is V of I union J. And in fact, you take any indexing set capital I or script I, and you take alpha collection of ideals, let's say, then zero set of I alpha, their intersection is actually the zero set of this union. So this is a subset in union of these ideals. This is running over some index set. For example, it could be IN, n belongs to n, countable, but it need not be countable, any collection, arbitrary collection. So that's why I'm doing it like example. So example, some. Okay. So so then V of this intersection of the zero sets is actually a zero set of the union. So this is V. This is the union. This is the union. Okay, and Vi union, so finite union, is equal to finite union of finitely many zero set is equal to product. So more generally, V of I1 union of j equal to 1 to n, let's say, and ij is v of I1, I2, In, the product. Okay. So it is closed under arbitrary intersection and finite union, and the whole set. So this resembles, if you think about it, closed sets for a topology. If you know these things, otherwise you don't bother. In F, okay, and this is called Zariski topology. You know such thing. It's not important to us, but uh, so more generally, so this is about so this is just a terminology. If you know already, this properties resembles property of a closed set for a topology in F. So the inverse, the whole set F is a closed set. The empty set is a closed set. Arbitrary intersection of closed set is a closed set, and union of finite union of closed set is a closed set. So such things we find topology on F, and it's called Zariski topology, but we don't need it. But more generally, for a field and a polynomial ring. So this is I just gave the example of one variable, but it need not be one variable. For a field F, and you take a polynomial ring F of x, sorry, um, you take a field F and you take and the uh, polynomial ring uh, polynomial ring in n variable. We can consider the zero set Vi for any subset I of f x1, x2, xn, given by V of I is a1, a2, an in Fn, such that f of a1, a2, an equal to 0. So similarly, uh, so it's a subset of Fn. So this is inside, if you like. So this is inside Fn. So this is inside Fn. For any subset I of the polynomial ring in n variables. So you take the polynomial ring in n variable over any field, and you take zero set of for any subset I inside this. You can consider zero set. So these are n tuples f to the power n, a1, a2, an, f to the power n, so that f of a1, a2, an equal to 0 for all f1, for all f inside this I. So again, the important point is here. This is a common zero. This is for all f. Every f should satisfy this. So it's a common zero for all the elements which are inside that. And again, some of these properties you can prove if I is subset of J, then Vj is a subset of Vi, arbitrary intersection, finite union, and for the whole. So, so now the question is, uh, uh, so let's see again. Let's see some many variable example. So this again we'll come back to this towards the end of the course. We'll study this. So let's say A in N, and consider, for example, you can take the polynomial ring in two variable qxy. You consider qxy polynomial ring in two variable over the rational number q, and inside that you consider this polynomial y square minus xq minus a, where a is a fixed integer in n. Then you can consider the zero set of this polynomial. So this is turns out to be set of AB in, so maybe not AB, set of x or alpha 1, alpha 2 in Q cross Q, such that uh, alpha 2 square equal to alpha 1 square plus E. Okay, and maybe, yeah, maybe I use alpha, maybe I use the notation alpha beta, maybe this alpha beta. beta square equal. Okay, this is this set. So for example, let's take a further special case of this. Let's take a equal to 1. So you take y square minus x cube minus 1 in qxy. Okay, so okay, so now it should have some space. So the subset of q cross q contains the point okay, so okay. Uh, Consider y square minus x minus 1 q xy. Then v of this is subset of q, and it contains the points. So for example, you can check this contains minus 1 0 x equal to minus 1 y equal to 0, x equal to 0 y equal to 1, x equal to 0 y equal to minus 1, x equal to 2 y equal to 3, and x equal to 2 y equal to minus 3. So now the question is, are these all the points? Okay, so question, and we'll come back to this later, the course, towards the end of the last few weeks in this course. So are these a question? Are these all the points in V of y square minus x cube minus 1? Okay, so we'll address this question later. Let's see another example. So you take again n be square free, fixed integer, fixed integer, and it is square free, and consider then v of y square minus x cube plus n square x, where fx y is y square minus x cube plus n square x, and this is again a polynomial. I'm considering two variable polynomial over cube. So this is nothing but again, so this is, you can write alpha beta belonging to q cross q such that beta square equal to alpha q minus n square alpha. Okay, it is this side. So for example, again, you specify n equal to 1 and fxy. So maybe this is where fn you can write. Here also fa maybe. Doesn't matter. So just a question of notation, y square minus x cube plus x belongs to qxy. So then you can see that v of this y square minus x cube plus x, of course 0 0 is there. Then you can check 1 0 is there and minus 1 is there. So now the question is, again, we ask the same question. So we ask this question, that question, are these all, so is this an equality, that is v of y square minus x cube plus x equal to 0 0 and plus minus 1 0. Okay, so this is the question mark. That is okay. So this is the question. Again, we'll come back to this question later. But let me end with this thing that in this setting, so consider a proper ideal in CX. Okay. Let's say 0 less than I less than Cx. 0, so I strictly contains 0, and it is strictly contained in. So it's a proper ideal. It's not the whole ring, and it's neither it is equal to 0. Then we can write I equal to fx, where fx is a, as I explained some time back, is a monic and non-constant polynomial. I can choose it to be monic. Then there is this alpha belong to C, so that fa equal to 0. So this is the fundamental theorem of algebra, right? Every non-constant polynomial over C, I have discussed this, that C is algebraically closed. So there exists a root of that polynomial. So which implies A is in Vi, right? If A is a root, then because this ideal is generated by F, any multiple of that will also vanish. Because F is vanishes, then F times anything will also vanish. So A is in V of I, okay? Uh, uh, So V of I is non-empty, and because it contains any root of this F. And let now I be a maximal ideal in Cx. Then what do you know? The maximal ideal, Cx is a PID. So any ideal, in particular the maximal ideal, is generated by an element, single element. The ideal is principal. And that ideal, because maximal ideal is prime ideal, this is a prime. This element is a prime element, hence it's a reducible element because it's a integral domain. Anyway, prime elements are reducible. So it is by some reducible polynomial, and again, as I explained, I can choose it to be monic. So then I can write fx equal to x minus a, right? Because the irreducible polynomial, what is the reducible polynomial? Cx, every polynomial has a root. So if the degree is greater or equal to 2, it will have two roots. So if the irreducible polynomial, it has to be linear polynomial. And since I assume it's monic, it has to be of the form x minus a for some a in C. Hence, all the maximal ideal of Cx are of the form x minus a. Right? So this is a simple fact. We saw two things. One, if we have a non-zero ideal, which is not all of the ring. If it's all of the ring, we have seen the zero set is empty. If it is zero, the zero set is all of C. So if I have a proper ideal, then this is non-empty. We have proven. And the maximal ideal of Cx are of the form x minus a. So both these things essentially follows from fundamental theorem of algebra, right? So this is essentially fundamental theorem of algebra. Algebra that C is algebraically closed. Okay, that's good. So then now you change the game. So now I'm asking more generally, you have the following fundamental theorem, and there's a name. It's called Hilbert's Null-Stellen-Satz. It's a German word. Hilbert was German. Satz means theorem. Null means zero. So it's like zero set theorem. So let F bar be an algebraically closed field. So we can think about C, for example. And if I have the n variable polynomial ring, f x1, x2, xn, and I be a, let's say, an ideal, because we consider zero sets, it's enough to think about ideals, which contains zero and strictly, and it strictly contains a proper ideal. Then this result I proved for n equal to 1 is true generally. Then Vi is a non-empty set, okay, of Fn. And this statement is equivalent to the maximal ideal of I have used the notation of bar. The maximal ideal of a bar x1 x2 xn are of the form x1 minus a1 x2 minus a2 xn, where ai belongs to f are arbitrary. So these two things are equivalent, and this is called Hilbert's Null-Snell's theorem, or the weak form of it. Although, yeah, okay. So, the contrast this contrast. So maybe I should just word of caution or contrast with R. So let's see, difference with R that if you take uh, uh, x squared plus 1 belongs to Rx is a maximal ideal, and V of x squared plus 1 is the empty set, right? We have seen, right? So that means this is that the thing is algebraically closed here is an important assumption. Otherwise, this is not true. Okay. But then for even for n variable, it's not very easy to prove. We have this important thing that the maximal ideal looks like x1 minus a1, x2 minus a2, xn minus a. Well, of course, this is easy to see. So maximal ideal really corresponds to a point, a1, a2, right? So, okay, the zero set corresponding to this is really a point. So points on Fn can be thought of as the maximal ideal of x1, x2, xn. And this is a fundamental theme in algebraic geometry, although we are not going into it. So, so the maximal, so it is what is easy to see that this is a maximal ideal. So you can prove that in Cxy, you have x minus a and y minus b, where a, b are arbitrary elements in C, and this is maximal ideal, and this is isomorphic to C, in fact. So this is the maximal ideal is not difficult to see, but all the maximal ideals are of this form. And this is a special thing about algebraically closed field. It is not true about Rx. Okay. So what we learned today is we defined that zero set of a polynomial. Given a polynomial, we can talk about a zero set, or more generally, any subset of a polynomial in one variable over a field. We talked about zero set. It is those elements of f where every polynomial in that subset I vanishes. Then the zero set is actually same as the zero set of an ideal generated by I. The zero set of the whole ring is the empty set, and zero set of the zero ideal is the entire F. And for R, we saw some examples. Zero set of a ideal which is strictly between 0 and Rx can be empty. And same with Q, for example. And the zero set might change. For the same polynomial, let's say x squared plus 1, zero set over R is empty, but over C it is non-empty. Or x squared minus 2 over Q it is empty, but over R it is non-empty. Over C it is non-empty. And we saw some properties which I have left as an exercise. You can do if I is a subset of J, then actually the zero set of I contains zero set of J. I is contained inside J, so it's reverse inclusion. And arbitrary intersection of zero set is a zero set. Finite union of a zero set is actually a zero set. And we can define the same thing for n variable polynomial rings. And then, for example, later in this course, we will come across examples of this. So you consider this polynomial, this type of polynomial, we'll see y square minus x2 minus a, where a is some integer or natural number. Actually, we'll consider integer. And yeah, maybe z, then we have to say a not equal to 0. I mean, as such, zero set can be defined for a equal to 0, but later in the course, we'll come across this kind of example where a is not equal to 0. So zero sets are those xy in q cross q, such that y square equal to x2 minus a. And yeah, and similarly, we saw some example that if you take y square minus x cube minus 1, then 0 set contains the point minus 1, 0, 0, 1, 0, minus 1, 2, 3, 2, minus 3. So the question we ask, are these all the points? So we'll not be able to give a proof of this, but we'll discuss this question. Okay. So yeah, so and then we said that if you take an algebraic closed field like C, then if you take a proper ideal, then the zero set is non-empty. Or the maximal ideal of algebraic closed field are of the form simple. They correspond to a point. They're always of the form x1 minus a1, x2 minus a2, xn minus an, where ai are arbitrary units of I. So next time we'll discuss algebraic integers. Thank you.